Okay, good evening, everybody. Welcome back. It's been a longer than intended break going to the field since before Christmas, but we are back. People have subscriptions and things to visit it. So good to see a lot of familiar faces and new faces in the audience. For those of you who haven't met me, I'm the coordinator. If you want to know about our events that are coming up this semester, go to neuniversity.org. There's mailing list there. You can sign up so I can spam you with interesting, relevant emails, not relevant ones, hopefully. But as we go through the semester, we have a series of talks, usually about every couple of weeks, for the scientific public. We're doing astronomy this week. We're doing awesome astronomy next week, because I'm doing the talk. And then throughout the semester, we're doing different things. It's not just an astronomy series, it's a physics series. We have some nuclear physics, some high-energy particle physics, new professors and things we've had during the university in the past couple of years. Talking about their research. And do sign up to come along to these things as well. So trying to do more things with the community as we go through as well. So hopefully as we go through towards the summer, we might be doing some events up here, but possibly down the library. Those counties on the library, they have a fantastic auditorium down there. So we might mix it up a little bit, but all of that information will be on the website. I will remind you that. And tonight it is my pleasure to welcome a visiting professor. Professor Kirby is joining the physics department officially in the fall, and then he's here now early, setting things up, getting his group ready, moving to South Bend in the winter from Caltech, where he wasn't sure. I feel that's a brave move. But you know, we're very happy to have him here. Evan got his undergraduate from Stanford back in 2004. He then went to UC Santa Cruz for his PhD, and then has been down at California Institute of Technology. He works on studying all kinds of things using the Keck telescopes and instruments, looking at stellar spectroscopy, looking at different colors of light coming from objects in the universe, looking at stars and things like that, telling us about their history, their galactic archaeology. So that is what he's going to tell us about. Let's do a nice warm welcome.
Thanks, Jonathan. Thank you. I am, in fact, a galactic archaeologist. You might be wondering what archaeology has to do with galaxies, and I'm going to tell you all about it. And the things that I use to do my archaeology are not picks and shovels and things like that, but the Keck telescopes, which I think very biased to the best telescopes in the world, and the summit of Mauna Kea on the big island of Hawaii. Now, this is not an example of a galaxy you can see from the Keck telescopes because it is in the southern hemisphere, but it's an example of the type of galaxy that I like to study, which are called dwarf galaxies. They're very small galaxies. In fact, this one has small in its name. It's called the Small Magellanic Cloud. There's two Magellanic Clouds, and if you've been to the southern hemisphere in a dark sky, you've probably seen them. These are two dwarf galaxies that you can see with your naked eye, the Magellanic Clouds. Now, this is a beautiful example of a dwarf galaxy, a beautiful example of any galaxy. It's got these nice dust lanes in it. It has this blue ionized gas. It has all these young stars. It's an absolutely gorgeous piece of art. That's not exactly what most dwarf galaxies look like. They mostly look like this, just kind of balls of stars. In fact, the technical name for this type of galaxy is a dwarf spheroidal galaxy. It's just a spheroid of stars. It's a fancy name for just a ball of stars. It doesn't have a lot of gas, little dust lanes. It's just kind of a glob of stars. Even this galaxy, which is called the Fornax dwarf galaxy after the constellation in which it lives, is a pretty exciting dwarf galaxy as dwarf galaxies go, because this is an even more typical dwarf galaxy. And if you're having a hard time seeing it, it's not your eyes. It's because these things are really small. That's why they're called dwarf galaxies. They don't have that many stars in them. And so the brightness of this galaxy isn't very much. And if you're having a hard time making it out, it's sort of this football-shaped thing that's going from the upper left to the lower right. Just sort of an overdensity, a small overdensity of stars there. And that's it. That's the whole thing. So the question is, why am I excited in these things that aren't very visually appealing? And it's because through the techniques of spectroscopy and archaeology that they actually have a lot of hidden treasures. But to show you, to set the stage of where these galaxies live in the universe, I want to show you a movie. This movie lasts a few minutes. I'm going to narrate through it. We're going to start at a place on the Earth that's very special, the Mount Everest, actually. We're going to leave Mount Everest. We're going to launch ourselves into space. we're going to get a setting for where these dwarf galaxies live in the universe. And in this movie, the dwarf galaxies are going to fly by in just a split second. So if you blink, you'll miss them. So get your tape ready, tape your eyeballs open, make sure you don't blink. But before we get there, we're going to really set the stage for the scale of the universe. First, we're going to set the scale for the stage of the size of the Earth, and then the solar system, and then our galaxy, and then the universe beyond our galaxy. So this is a beautiful movie made by the American Museum of Natural History. And the first thing we're going to do when we zoom out is we're going to see the artificial satellites that orbit the Earth. These are satellites that human beings have launched to do things like GPS, communications, all sorts of cool stuff. And occasionally on the bottom, you'll see the light travel time from the Earth. Once we start zooming out beyond the solar system, you're going to start to see how many light years we are from the Earth. But as promised, the first thing you're going to see is the orbits of the artificial satellites. It does not include the now infamous Starlink satellites, because this movie was made before Starlink came into existence. These are just a fraction of the satellites that orbit the Earth. And you notice how there's this kind of light blue line in the background. When we zoom out a little bit more, you'll see that's actually a ring around the Earth. Anybody know why there's a ring around the Earth of satellites? Why would there be a special ring? And in fact, it's around the equator. That's correct. Those are the geosynchronous satellites. There's a special spot that's a certain distance from the Earth, and it's around the equator. If you put a satellite there and orbit around the Earth, it'll stay above the same point in the Earth because the orbital speed of that satellite is equal to the rotational speed of the Earth. Those are called geosynchronous satellites or geostationary satellites. So let's zoom out a little bit, and we're going to start to see a little bit more of the solar system. That's the ring of geostationary satellites. And now this red line that you see coming across there, that's going to be the orbit of the moon. And everything here is to scale. And so that's the size of the Earth compared to the size of the orbit of the moon. We're going to zoom out a little bit more. That green line trailing behind the Earth is the orbit of the Earth around the sun. You can see the other planets in the solar system coming into the vision. We're going to continue to zoom out. As we zoom out, we're zooming out faster and faster and faster. And that's going to be the theme for this whole movie is we're going to go out faster and faster and faster. You see now where the light travel time from the Earth, we're only one light hour away from the Earth. We're going to go faster and faster. We're very soon going to be a light year away from the Earth. You see the lines of the constellations? They only look like that from the Earth. So as we zoom out farther and farther and our perspective changes, you'll notice that the lines that connect the constellations are going to start to warp because we're actually going to see their 3D position within the Milky Way galaxy. And now we've faded out the sun to be of the same relative brightness as all the other stars in the sky. So that's how it actually looked if we were this far away from it. Now, remember when I said you can't blink, you're going to miss those dwarf galaxies? It's coming up in just about half a minute from now. That's how far the radio signals from the Earth have ever made it so far. So 70 years ago, we had radio signals leave the Earth. We're zooming out of the Milky Way disk now. You're about to see a picture of the Milky Way. This isn't a real picture of the Milky Way. This is how we think the Milky Way probably looks. And be careful, we're going to see those dwarf galaxies. Little green dots are coming in now. You see those things right there? Those tiny little blips are the things that I've based my whole career on, those little dwarf galaxies. We're going to see them come back again because we're going to zoom out throughout the whole universe and see them come back again. Every one of these green and red, all these different colored dots is a galaxy in the sky. So every one of these things is a galaxy. And you can see how many billions of galaxies we've actually mapped so far. Now, these regions that don't have galaxies, it's not because the universe decided not to put galaxies there. It's because we live in the Milky Way, and it's hard to see through the plane of the Milky Way because there's a bunch of stuff in the way. And so we can't actually see those portions of the universe. They're hidden from our view. And in fact, you can also see how the galaxies seem to taper away as you go farther and farther away. It's not because there aren't galaxies there. It's just because as you look farther and farther away, they become fainter and fainter and harder to detect. And so you can see some of the observational biases of how much we know about the universe and how much we don't know about the universe. This very brightly colored sphere is how far we can possibly see, given the limits of physics. It's called the cosmic microwave background. That is for a subject of a totally different talk. But now we're going to zoom back in and get closer and closer back to the sun again. And as we get back close to the Milky Way, I want you to look one more time for those dwarf galaxies because they're really the focal point of this talk. We're zooming back in. You can see we're zooming back in along the plane of the galaxy, the part of the universe we haven't mapped as well. This little cluster of green points in the center of the screen here, that's called the local group of galaxies. It's dominated by the Andromeda Galaxy, which is over here. This is the Andromeda Galaxy, and the Milky Way. And all these green points around it, those are the dwarf galaxies. Those are my friends. Those are the ones that I've spent so long at the Keck telescopes looking at. And then we're going to zoom back in to the sun to give you a sense of scale for the universe and where these dwarf galaxies live. Now you notice all the dwarf galaxies I pointed out, they live pretty close to the Milky Way. Again, that's an observational effect. These dwarf galaxies are all over the universe. They're the most common type of galaxy in the universe. Galaxies like the Milky Way, they're not rare, but galaxies like these dwarf galaxies, they're incredibly common, much, much more abundant in the universe than the Milky Way is. That's also a great reason to study them because there's so many of them. These galaxies literally litter the local group. There's so many of them. So the local group of our galaxies is dominated by the Milky Way and Andromeda, and each of those two large galaxies has its own groupies, these little groupies of dwarf galaxies that orbit around it. And each one of them has its own little secret treasures inside of it. And the only way to really see what those secret treasures are with the magic of spectroscopy, which we'll get to later in the talk. Let me give you a sense of scale for these dwarf galaxies. If I establish a conversion rate between stars and people, like let's say I want to convert US dollars to euros or something. There's a conversion rate associated with that. I'm going to establish a conversion rate between stars and people. The Milky Way has about 50 billion stars in it. And New York City has about 8.2 million people in it. So if I say that the Milky Way is sort of a New York City-sized galaxy, let's get a sense of scale for what these dwarf galaxies look like. That first dwarf galaxy I showed in the title slide is called Fornax because it lives in the constellation called Fornax. It has only 19 million stars. 19 million sounds like a big number, but it's a heck of a lot less than 50 billion. And so we're using the same conversion rate between the Milky Way and New York. Fornax is equal to this little town in Pennsylvania called Strasbourg. How do you count the number of stars? That's a fantastic question. We don't go there and we count one by one and get up to 19 million. We actually look at the total light emitted from the galaxy, and we have a good sense of a conversion between the light of the galaxy and the mass of the galaxy. So we actually measure the light from the galaxy and we use a conversion called the mass to light ratio. You multiply the light by the mass to light ratio and you get the total mass of stars. And the total mass of stars gives you a good sense of how many stars there are. I should also say that as with many things in observational astronomy, these numbers are not exact. That 19 million, it's not even precise to the number 19. It's probably 19 million plus or minus 4 million. So it's always pretty big error bars on these numbers. The 19 million stars using the same conversion rate is only about 2,800 people. It's a little town in Pennsylvania called Strasbourg. Anybody here been to Strasbourg? I didn't think so. It's a tiny little town in Pennsylvania, which gives you a good sense of how small these galaxies are. It's very rural type galaxies. And remember I said Fornax was actually one of the larger of the dwarf galaxies that lives in the local group. Another galaxy, Ursa Minor, which is found in the constellation Ursa Minor, is even smaller. It has only 560,000 stars. There's a huge contrast between 50 billion stars and 560,000 stars. So Ursa Minor is equal to this town in Montana called Loma, which I'm pretty sure no one's here has been to or even heard of Loma, Montana. It's a very rural place. And that's kind of what Ursa Minor is. It's this sort of corner of the local group. There's not a lot of stars there, but it's still interesting to visit. I'm sure the people of Loma, Montana are great people, and they have great stories about, I'm going to guess, ranching. And so the stars in Ursa Minor have great stories about what they were doing and how they lived their lives. I like to think of these galaxies as little factories. Now, a lot of these towns, a lot of these rural towns are built around factories. These dwarf galaxies are also built around factories. And the type of factories that they have are called supernovae. The supernovae are the factories of the chemical elements of the periodic table. And so every time you form a population of stars in these galaxies, some fraction of those stars is going to explode. And when they do explode, they're going to create the heaviest elements of the periodic table. So this is an example of a simulation of a star exploding. This is such an active field of research that people actually model this in their computers. How does a star explode? They model that in their supercomputers. And so what you see here is one example of how a star might explode. There's this little detonation that happens in the center of this star. This is a particular star called a white dwarf. And that detonation kind of pokes its way out to the surface of the star. And from there, that flame will engulf the rest of the star. And in the process of this whole explosion, the densities and the temperatures of that star are getting so hot that you literally take the atoms inside of that star and fuse them together. So you can imagine like inside of the factory on the Earth where you have really hot temperatures to melt metals and fuse them together and make alloys. The analogy here is that you get to temperatures and densities so hot that you literally take the nuclei of the elements and you merge them together to make heavier nuclei, to make heavier elements in the periodic table. So you start with really light elements like hydrogen, you make helium. You take helium, you merge it together, you can make carbon. And in this case, we're taking carbon and we're smashing a bunch of carbon together to make stuff all the way as heavy as iron and nickel. And so this is just one example of a factory in this galaxy, but you put a bunch of these factories together and you have a whole story of evolution of a galaxy. So this is a simulation by my friend John Wise at Georgia Tech. And what I really like about this simulation is that he's processed the light of the simulation through the colors that you would actually see with your naked eye. So this is not a false color simulation. This is a simulation of a galaxy, how it would actually look, the real colors of the galaxy. And so all that red light is hydrogen gas because hydrogen gas glows red. And all this blue light is oxygen gas because oxygen gas glows green, it glows blue. And then the green stuff is sulfur. And so you can see all these different elements being formed very viscerally because that's the actual color that they glow. You start off with the lightest element, hydrogen. And then when that first factory starts its production, then you start to make oxygen, you start to make sulfur, and you can actually see that happen when that supernova goes off in the center of the galaxy. And you can put a bunch of these different factories, a bunch of these different supernovae together, and you have yourself a story. You start off with the lightest elements of the periodic table, you make heavier elements, you take those elements and you make even heavier elements, and you keep going and going and going until you make more and more of these heavy, heavy elements. Now, these dwarf galaxies, it seems like they were really productive, right? But unfortunately, like a lot of factory town stories, the factories were once in heavy production and like people had jobs, people were happy. But like a lot of Rust Belt towns, the factories are now dead. So these dwarf galaxies were doing their thing a long time ago. When I say a long time ago in the Rust Belt, that means a few decades ago. But for these dwarf galaxies, it means 10 billion years ago. That's how long ago these factories were in operation. They were doing their thing. They were really taking those lighter elements and fusing them into heavier elements, and they were doing it in earnest. But then for some reason, one day, the foreman shut the place down. All the workers lost their jobs. They had to pack up and move out, and the galaxies have just been decaying and rotting since then. And so the galaxies now left over, all we have left is just sort of the remnants of these factories. All we have left is sort of the material that's been strewn about, that's been left over from what these factories were doing 10 billion years ago. They're not in production now. So how do we know what these factories were doing? How do you know? How can you like walk through this factory and tell what kind of thing that they were making? Well, one way you can do it is with archaeology. So you can imagine like a civilization, like if you go to Haifa, Israel. I think this is Haifa. Has anybody been in Haifa? You can tell me if this is Haifa. I think this is Haifa. It is an archaeological site where there was once a very thriving civilization. You can imagine that you were walking around this civilization or this archaeological site and you find a piece of pottery on the ground. And you want to know, what were these people doing with this pottery? Clearly they were making something and they were putting it in this vessel, but you want to know what that thing was. Were they making wine? Were they making olive oil? Caleb, what would you do if you found a piece of pottery and you wanted to know, what is this substance on it? Is it oil? Is it wine? How would you test that? Say again? You could do mass spectroscopy. That's cool. Yeah. So what that is that you actually take the atoms in this thing and you pass it through something that tells you how heavy the atoms are. Caleb, what would you do? Do you have any idea if you wanted to figure out what this substance was? You know what I would do? I would lick it. I would see if I could taste it. I can tell if it was wine or olive oil or something. That's probably not the most advisable idea. There'd probably be some safety things that you'd probably have to go through before you start licking the pottery you find at Haifa. So mass spectroscopy is a better example. And in fact, archaeologists have tools like mass spectroscopy. And so I fancy myself an archaeologist. And so like any good archaeologist, I have a leather hat. But unfortunately, I can't actually go and walk around and find artifacts on the floor in my dwarf galaxies. All I have is the light from the dwarf galaxies. All I have is these stars that are shining here like this. And archaeologists, they have tools, or terrestrial archaeologists, they have tools that look like this. They can brush off that thing, they can lick their pottery, but I can't go lick a star. I don't know if I'd want to. Actually, I kind of do. That'd be pretty cool, but I can't. So instead, what I'm stuck with are these tools. These are the two twin Keck telescopes on the summit of Mauna Kea in Hawaii. And this is where I do my archaeology. Now, the two twin Keck telescopes, they're called twins because they're pretty much the same telescope, mirror images of each other. They built one and they said, why build one when we can build two for twice the price? And so we have two telescopes now and we have different instruments behind them. And the type of instrument that I like to use is called a spectrograph. This is where you take the light of the star and you split it up into its component colors. Now, this is an example of a spectrograph called high-res that Professor Weiss over there, it's her favorite spectrographs, I'm pretty sure. It goes from red light to blue light, but high-res doesn't just have a few colors. It has more than just red, orange, yellow, and green, and blue. It actually has red number 4,446, red number 4,447, red number 4,448, and so on. So you can count up all the different colors that high-res can see. And it's something like 20,000 different colors that high-res can resolve. And if you plot all those colors from left to right, you go from the reddest light to the bluest light, you can see that this particular star is really bright in some of the colors, and it's really faint in some of the other colors. And the reason is that some elements really like to suck up very specific colors of light. These are called absorption lines. So elements like, for example, hydrogen. Hydrogen really likes to suck up the red light. So you see about the fourth row down there, there's this huge chunk of red that's missing, that very specific color of red that's missing. That's because hydrogen is in the spectrum of this star, and the hydrogen is sucking up those colors of light. And you see down here, there's three missing pieces of green in the same row. That's because magnesium really likes to suck up those very specific colors of green. So I can tell just by looking at this spectrum, this star has hydrogen, it has magnesium. Up there, I can see some sodium. All these different colors that are taken out of the spectrum are because these different elements are present in the spectrum of the star. This is the spectrum of everybody's favorite star, this is the spectrum of the sun, that's right. And so the sun, this is a sitting duck. You can easily take a spectrum of the sun because it's so, so bright. But the stars that I'm looking at are trillions of times fainter than the sun. So I really need a very sophisticated, very big telescope to look at these stars, and that's what the Keck telescopes offer me. Now, this is a really awesome example of a stellar spectrum because it can resolve 20,000 different colors. But in order to do that, you need a lot of light. You need really bright stars. So instead, I go to a different spectrograph on Keck. It can't see quite as many colors. In fact, it can't even see the same range of colors. So it sort of starts at yellow and goes to red, and actually goes beyond the visible spectrum into the infrared portion of the spectrum. But even in that portion of the spectrum, you can still see the signatures of a whole bunch of different elements, as I'm about to show you. This is what the instrument looks like. It's about the size of a small school bus. You can see these people standing here like this. This isn't like the kind of telescope you want to go and put an eyepiece on and look through it, because the beam itself is like this big. And the beam that enters this spectrograph here. And because the telescope has to move to track the sky, the stars rotate in the sky. The stars rise and they set. And because they do that, the whole field of the starlight is rotating like this. So this whole instrument, while it's looking at the sky, is also rotating. That's really not very good when you're dealing with very precise measurements of light. And so there's actually a flexure compensation system in here that can keep a speck of light to within 1/10 of a pixel. And the pixels are only 15 microns big. That's 15 thousandths of a millimeter. So that's how precise this instrument is. It's ridiculously precise. It can keep a speck of light to within 1/1000th of a millimeter, even though this whole thing that's the size of half of a school bus is rotating 180 degrees over the course of the night. It's an incredible piece of engineering, and I'm really thankful for the people who designed this and built it and maintain it. The Keck Observatory, I'm telling you, the best in the world. This is what a spectrum looks like. This is what an image looks like from the DEIMOS spectrograph. The cool thing about DEIMOS is even though it can't see as many colors as high-res does, it can take spectra of about 150 stars all at the same time. So every time I open the shutter of the DEIMOS spectrograph, I can see the composition of 150 different stars in one of these dwarf galaxies. Now, this is literally just a camera. It's like the camera in my phone. So I looked up how many megapixels are in the camera in my phone here. It's like 50 megapixels, some really fancy phone that I have here. You know how many megapixels are in the DEIMOS spectrograph? It's actually about the same number. So it's maybe not that impressive how many megapixels it has, but that gives you a sense of what this thing actually is. It's really just a digital camera. But it's a digital camera that can see colors very exquisitely. And let me zoom in what you're looking at here. If I zoom in really close, you can see a bunch of lines that are moving from left to right. So these horizontal lines. Every one of those lines is the spectrum of a different star in a dwarf galaxy. And we zoom in really, really close. Oh, sorry. And this is about as close as I'm going to zoom in. You also see these these vertical lines that go up and down. That's actually a spectrum of the Earth's atmosphere. And so unfortunately, we terrestrial astronomers have to deal with this pesky thing like the atmosphere. Yeah, I guess I'm grateful that I can breathe, but it really gets in the way of having to observe these stars because the skylight, even at night, glows. And it glows and it has all these emission lines in it, and I have to get rid of those things. And so we can do some fancy image processing to get rid of the Earth's signature. What we're left with is just the stars. So these are the stars in the dwarf galaxies. Professor Wenninger. Oh, fantastic question. Why are those lines not the same? So what Professor Wenninger has asked, like, I have different spectra of all these different stars. How come if these vertical lines are from the Earth's atmosphere, why don't they line up with each other? Why aren't they all the same? And in fact, they should line up with each other. They absolutely should. But what happens when we actually observe with the spectrograph is we can observe a star here and we can observe a star here. And what that does is that actually changes the 0 point of the wavelength scale. And so this wavelength here in the bottom row corresponds to this wavelength here in the second to bottom row. Yes, that's right. So it's just the offsetting of the wavelength scales. It's the only thing that's going on there. So this is what the spectrum of the individual stars in one of these dwarf galaxies looks like. And you can see every now and then there's a chunk taken out. Can you see how there's little divots taken out of each of these lines? Those are the absorption lines. And in fact, this is the element calcium doing its job. The element calcium really likes to absorb these three specific colors of light. This one here, and this one here. So I can tell that there's a lot of calcium in all of these stars because they're absorbing the light at those very specific wavelengths. Now, it's very difficult to look at this thing just sort of an intensity map like this. And so when we actually look at spectra, what we like to do is plot the amount of light we see versus the color that we're looking at. And the color we're looking at, we call it the wavelength. And we assign numbers to each color. That number is equal to the wavelength of the light that we're looking at. And you can see that there's not very much intensity of light at these very three specific wavelengths, again, due to the presence of calcium in this star. And this is a spectrum, the full spectrum of one star in the Sculptor dwarf galaxy. It's called the Sculptor dwarf galaxy because it lives in the constellation Sculptor. And you can see there's a whole bunch of absorption lines all over the spectrum of this star. And these absorption lines are color-coded now by the element that's responsible for doing the absorption. So you can see, I can see iron, I can see magnesium, silicon, calcium, and titanium. I can see all of these elements and figure out what the star was made of. And so the periodic table is really my oyster here. I can really figure out all of the different elements of the periodic table in the star. Actually, it's a bit of an exaggeration because most astronomers, when they look at the periodic table, they see hydrogen, helium, and everything else. We literally call everything else metals. Yes, even oxygen, we call it a metal. Chemists hate this, and they should. It's a terrible nomenclature. They're not metals, but we call them metals anyway. In the interest of time, I'm going to skip through this part a little bit. My apologies. And I'm just going to say that the elements that I can see very easily with my DEIMOS spectrograph are hydrogen, magnesium, silicon, calcium, titanium, and iron. With those 6 elements, I can really tell you a lot about the history of these dwarf galaxies. This is how I do my archaeology. It really boils down to this. Those first 4 elements, magnesium, silicon, calcium, and titanium, they form a group called the alpha elements in the periodic table. And the alpha elements are very special because they come from a very specific type of factory, a very specific type of supernova. These are the supernovae that happen first in the galaxies. These are the workers that show up to their job early in the morning and say, I'm ready to make my production schedule. And the first thing that they make early in the morning are the alpha elements, not so much iron. And so if I plot the amount of alpha to iron, the ratio of alpha to iron that's produced in these first supernova, then pow, when that first supernova blows up, we make a lot of these alpha elements, magnesium, silicon, calcium, titanium, not too much iron. And as the day goes on, we make more and more of these elements in about the same ratio. But if I plot just the amount of iron on the x-axis, we're making more and more iron, but in the same ratio with the alpha elements. But then if you wait long enough, then the lazy workers, the afternoon shift, they come in and are like, okay, what are we making today in the factory? And these late shift workers, they're a totally different type of supernova. And they're so lazy, they don't even bother making the alpha elements. They only make the iron. And so when those supernovae blow up, they're kind of a rowdy crowd. They really like to drop F-bombs. Sorry, I meant to say Fe bombs. They're iron bombs. And when they explode, they make tons and tons of iron, but very, very little alpha. And so the alpha to iron ratio is going to drop dramatically in these galaxies. And so depending on exactly the shift schedule of these workers, we're going to see different patterns in this diagram. This is called the diagnostic plot for galactic archaeologists. Let me give you an example. This is the galaxy called Draco. It was really, really terrible at its job. Its job is to very efficiently take gas, make supernova, and turn it into new metals. Take hydrogen gas, make supernova, and turn it into new metals. And if it does it very efficiently, then it keeps that alpha to iron ratio up. It makes lots of magnesium, lots of silicon, lots of calcium, lots of titanium. But if those late shift workers are straggling in, and they don't bother making the first 4 elements, and they only make a bunch of iron. And so this galaxy was really bad at its job, because what you see is that the alpha to iron ratio just can't maintain that alpha to iron ratio. It's just going to make lots and lots of iron. This is a different galaxy, Sculptor. It was slightly better at its job because it maintained a higher alpha to iron ratio for a longer time. But even in the end, it still got very lazy and started making a bunch of iron. So just by looking at these 2 diagrams, I can tell you that even though these galaxies both stopped forming stars 10 billion years ago, Sculptor was at least a little better at its job than Draco was. This is the archaeology part of this. By looking at the composition of the galaxy, I can tell you that even though these galaxies have been dead for 10 billion years, Sculptor was better at its job than Draco. And finally, we have Fornax, which I would say has sort of an erratic production schedule. If I was the foreman for this factory, I would say, this worker is sometimes good and sometimes not very good, because this is actually a valid track through the alpha to iron diagram. I could make you a model that explains this particular data set. It looks like this. That sometimes the galaxy was very lazy and wasn't making very many alpha elements. And then they woke up and was like, oh my gosh, the foreman's looking over my shoulder. I better make some alpha elements right now. And then got lazy again when the foreman went away. And when the foreman came back, was like, I better make some more alpha elements now. And so it's a very erratic production schedule. This is also a valid track through this diagram. These look like just squiggles, but I could actually make a chemical evolution model that looks like this. And so here the galaxy was really good at doing its job, and then it just stopped. And then it refilled with gas and started over again, and it was a little bit lazier the next time around. But what I really think would happen with Sculptor is that it's really sort of got a split personality, where some parts of the galaxy were really good at doing its job, and other parts of the galaxy were not so good at doing its job. And so really you're looking at different parts of the galaxy all put together to make one bigger dwarf galaxy. I'd like to wrap up a little bit now and tell you about a very special dwarf galaxy that was discovered maybe 15 years ago. You're actually looking directly at the galaxy. It's really hard to tell that you're looking at a galaxy there. It just looks like a bunch of stars, right? Because most of the stars in this figure are actually just field stars that are in the Milky Way. The problem with finding these really tiny dwarf galaxies is that we are doomed to live in the Milky Way, and we're always going to live inside of the Milky Way. In order to find the galaxies outside of the Milky Way, we have to look through the Milky Way. And so there's stars in front of our faces that are really kind of obscure the view for the galaxies behind. With the magic of spectroscopy, I can tell you which stars in this image are members of this galaxy called Segue 1. It's these. You would never be able to tell that just by looking at this image. But with spectra, I can tell you which stars are moving together with respect to each other, which stars have the same velocities in the plane of the sky. And actually, with the magic of image processing, I can get rid of all of the other stars that are in the foreground, the members of the Milky Way. What we're left with is just this smattering of stars that itself is actually a galaxy. For a time, this was the smallest galaxy that we knew about. It's now been usurped many times over because astronomy moves on, we make more progress, we find even smaller and smaller galaxies. But if I were to put Segue 1 on the same conversion between stars and people, remember the Milky Way, 50 billion stars, New York City, 8.2 million people. Segue 1 has about 1,000 stars, and so it's like a tenth of a person. It's really that tiny. It's a ridiculously tiny galaxy. And it really challenged what we thought a galaxy was. Like, it really made us think. Actually, it was this galaxy inspired a paper called Galaxy, Defined. We had to come up with a definition for a galaxy just to explain what this thing was, to distinguish it from something else called the star cluster. So despite the fact that this galaxy is so ridiculously tiny, you can paint a story that we did, this archaeological story. You can look at the composition of its stars and figure out what kind of production schedule it had. You can also do other things with the spectra of the stars, like measure their velocities and figure out how much dark matter is inside of this galaxy. It turns out that this is one of the most dark matter dominated galaxies that we know about. The ratio of dark matter, the matter that we can't see, but we know it's there from the motions of the stars, the ratio of the dark matter to the luminous matter, the stars, is the highest in any galaxy that we know about. And this is Segue 2. It's the cousin of Segue 1. It's a similarly sized galaxy. In the background, you're looking at the point that you saw a few slides ago for the Draco dwarf galaxy. And so the question I wanted to ask was, do these really, really tiny, what we call ultra faint dwarf galaxies, have any different kind of archaeological evidence that they had different production schedules than more run-of-the-mill dwarf galaxies? And the answer is no. So when I actually measure the composition using DEIMOS of individual stars in the Segue 2 dwarf galaxy, they lie right on top of the pattern that's established by more typical dwarf galaxies. And so even for these really tiny galaxies, the magic of spectroscopy tells us that they sort of had the same story as its much, much larger cousin. So that was very interesting for us to find out. So I really appreciate your attention. If you take away only 4 points today, remember that galaxies are factories, and their products are the chemical elements of the periodic table. The Keck telescopes and other telescopes, but mostly the Keck telescopes, can dig up the archaeological evidence for what these galaxies were doing through the magic of spectroscopy. That spectroscopy can tell us what the stars are made of, and those stellar compositions could reveal the past production schedule for these galaxies. And finally, even the tiniest galaxies like Segue 1 and Segue 2 manufacture chemical elements in a manner very similar to their larger counterparts. They're just smaller examples of the same dwarf galaxies. Thanks very much.